Hello everyone, welcome to another episode of the course Software Defined Networking. In today's lecture, we will explore the application plane of the SDN architecture. The objective for this week are that at the end of this week, you would be able to present an overview of the SDN application plane. You will also understand the concept of the network services abstraction layer. This concept will allow you to explain three forms of abstraction in SDN that is commonly in used. And finally, you will be able to list and describe some application areas where SDN is playing an important role. So the power of the SDN is in the support that it provides for different types of application and services. And you know that the SDN control plane provide the functions and services that facilitate the rapid development and also deployment of the network applications. So in this lecture, we are going to explore these concepts. Here is a brief roadmap for this lecture. We will start by giving or by providing an overview of the SDN architecture, and this is the first topic of our journey into the world of SDN. So we will have a recap of the SDN architecture and the different layers of the SDN architecture. And after that, we will be focusing on the SDN application plane and the network services abstraction layer, and then we will discuss some applications like traffic engineering, security, data center networking, and ICN, information centric networking. These are some emerging applications for the SDN. So let us start with an overview of the SDN architecture. We have covered the SDN data plane, and then we covered the SDN control plane or the SDN controller, different types of APIs and functionalities that it provides. Now for today's lecture, we will explore application plane in details, and we will see different types of application which are related with security, network services, and also some business application related to data center, cloud computing, and information centric networks. So this is going to be the focus of our presentation for this week. SDN application plane. This is actually the architecture of this first plane or first layer, that is the application plane. What is inside it? Let us see them one by one. The first thing is that the application plane contains different applications and services. These applications and services will define, or it will explore how we can actually monitor and control network resources and network behavior. We will see that these applications will actually interact with the SDN control plane with the help of application control interfaces. In this figure, you can see different types of interfaces like the northbound local interface, remote interface, user interface if the user is local, and an interface support for the user if the user is remote. And also you can see different types of applications or functions or services like the data center, mobility, information centric networking, security, measurement or monitoring, and traffic engineering. Let us start discussing this architecture for the application plane from the bottom. First thing is the northbound interface. You can see here we are going to talk about this interface. Although we have discussed a little bit about this interface while we were studying the control plane. Let us see it from the point of view of the application plane. Actually, this interface, the northbound, it will enable applications to have access to the control plane functionalities and their services. But the good point is that it will not need to know the details of the underlying network SDN switches. Because abstraction is there, details should be hidden from the layers above it. This interface actually provides an abstract level view of the network resources that are controlled by the software in the SDN control plane. As you can see, this interface can be either local or it can be remote. Local interface means that the SDN applications are actually running on the same machine as the control plane software. While on the other side, the remote northbound interface means that actually the application can be running on a remote machine or a remote systems, you can say. And one of the well-known example, as we know, for this northbound API is the REST API, and we discussed about the REST in our previous lecture. Above this interface, we have the network services abstraction layer, and this is defined in one of the RFC, that is 7426. This RFC actually defines this network abstraction layer, and this layer is actually between the control and the application planes, and it describes it as a layer that will provide the service abstractions. Actually, this layer will provide an abstract view of the network resources, and it will hide the details of the underlying data plane switches or devices. In other words, you can say that the network services abstraction layer will actually provide a generalized, a top level view of the control plane functionalities. Why we need that? So that our applications on top of it could be written that would operate across a large number of network operating system or network devices or manufacturers built-in switches. We will see that this functionality of the network service abstraction layer is actually similar to that of the concept of a hypervisor, or also known as virtual machine monitor, that also decouple applications from the underlying operating system and underlying hardware beneath that operating system. So in a similar way, this abstraction layer will provide a generalized view of the control plane functionalities. You can say that the network services abstraction layer could be considered to be part of this interface, not as a separate layer. And also the functionality is incorporated in the control plane rather than the application plane. Okay, so that is also possible to do that way, but in our architecture that we are going to study, we consider that this abstraction layer is actually part of the application plane architecture. Then we have different types of network application on top of that, and that is the actual things that happens at the application plane. Many different network applications could be implemented or could be deployed for an SDN, and in this figure you can see 6 categories of them, and they are the data center related, traffic engineering related, mobility and wireless, measurement and monitoring, information centric, and security. We will not cover all these applications, but we will shed some light on data center, on traffic engineering, on security, and also at the end we will explore the concept of information centric network. So we will come back to these applications at the final stages of this presentation. And then the other component is the user interface. Actually, as you know, that interfaces enable a user to configure different types of parameter in the SDN applications, and it enables the user to interact with the applications itself. And you can see two possible types of interfaces. There is local and remote. The concept is same. If a user um, is in the same, or if the user is using the same machine or server, for example the server devices, keyboard, the monitor, etc., then there is an example of a local interface. But if the user log in to the server from a remote area, to the application server from a remote area by using a communication network facility, then that is going to be the example of a remote user interface. Okay, after discussing the application plane architecture, we are going to explore the important component, that is the network services abstraction layer, in details. So our next slide is about network services abstraction layer. During this course, we talked a lot about the abstraction layer. Actually, the abstraction is a concept that refers to the amount details about the lower levels of any model that is visible to the higher level. In reality, more abstraction means less details of the underlying hardware, and less abstraction means more details about the underlying hardware or resources. So the more abstraction, which means the less details, is an important design principle for SDN. On the other side, the abstraction layer is actually a technique. It is a mechanism that will translate high level request, like the application layer request or the user request, into low level commands that the hardware, that the switches can understand. And these commands are issued to perform certain tasks, or to perform or to take action on the request generated by the user. And the API that we are studying, for example the REST, OpenFlow, etc., there is one such mechanism to achieve this objective. Why? Because it will hide the implementation details of a lower level of abstraction from software at a higher level. And we know that a network abstraction actually represents the basic properties or characteristic of network entities. For example, switches, different types of links, interfaces, ports, and flow of data, in such a way that the network programs can focus on the functionalities without having to program the details action for the lower level. So you actually concentrate, being a developer, on the higher level aspect of the development. Well, abstraction in SDN, let us see. SDN can be defined by three fundamental abstractions: forwarding abstraction, distribution abstraction, and specification abstraction. And these are mentioned here: forwarding, distribution, and specification. Let us discuss them one by one. First, forwarding abstraction. And we are quite familiar with this concept because it will allow a control program to specify data plane forwarding behavior, but it will hide the details of the underlying switching hardware. And why we need this forwarding abstraction? Because it provides flexibility and vendor neutrality. And we have seen that one of the student was talking about it, that we have different manufacturer devices at the physical level. So we need an abstraction that our solution will work for all these different vendor devices, and that is known as vendor neutrality. Similar is a concept with net neutrality. If you are interested, you can explore it on your own. And this forwarding abstraction is normally implemented with the help of an API, southbound API, and that is the OpenFlow. Second level of abstraction is between the application plane and the control plane, and that is known as the distribution abstraction. As the name indicate, actually this concept arises in the context of distributed controllers. We know that more than one SDN controller are possible for large enterprises. So a cooperating set of distributed controllers, they actually maintains a state description of the network and routes through the network. So controller, if there are more than one controller, they must cooperate to maintain a consistent, logical and global view of the whole network. But this must be hidden from the upper layer. So this abstraction, the distribution abstraction, actually the objective is to hide complex distribution mechanism. And due to this abstraction, we will have a single coherent global view of the network. And one such example of such implementation or such abstraction is the Northbound API REST. And if we talk more specifically about the networking abstraction layer, the network operating system is another example, and we studied about that in Open Daylight architecture. Finally, we have the specification abstraction. As I just mentioned, the distribution abstraction actually provide a global view, logical view of the network. And you will see that there exists a single centralized controller rather than distributed controller, although there are more than one distributed controller. But you will see them that there is only a single centralized controller, even if multiple cooperating controllers are used. So that was the functionality of the distributed abstraction. On the other side, the specification abstraction, this will actually provide an abstract level view of the global network. It will provide enough detail for the application to specify their goals, such as routing policies, security policies, trust related policies, forwarding policies, etc., without providing the information needed to implement the goals, because these are low level details and we are not interested in those low level details. Okay, so actually there are you can say that 3 level of abstraction or 3 level of interfaces for those abstraction. The forwarding abstraction actually hide the low level details, forwarding hardware details from the higher layer. The distribution layer actually hide, for example, the distributed nature of the SDN controller. It provide a global network view, and the specification abstraction will actually provide a network view to the application, a single network global view to the application, and it will hide the physical network details from it. And this example, this figure, this scenario is actually a simple example of the of these different types of specification. The physical network is actually, you can see, is a collection of interconnected SDN control plane. The abstract view, however, is a single virtual network, and at the lower level a single virtual switch. Okay, so let us see another example of the abstraction in SDN. This is actually this figure focuses on the specification abstraction. We studied 3 types of abstraction, so this actually focuses on the specification abstraction, and you can see that at the application, at the data layer, we have different switches. This is actually the physical network, which is a collection of different switches, and on top of that we have only a single virtual switch. This is possible because of the abstraction. The abstract view is like a single virtual switch, although we have multiple switches at the physical network, but the details are hidden. Now let us see a real example of the network services abstraction layer from implementation, like the implementation of the network services abstraction layer. And this is known as a frenetic architecture. It is an example of the network services abstraction layer, and this is actually a programming language which enable a different type of network related entities like network operators, network designer, policy maker to program the network as a whole instead of manually configuring these individual network elements. You can actually configure the network as a whole. This frenetic was initially designed to solve challenges that were related with the use of the open flow based model. Okay, uh, because if you are working with open flow, then you must know that it works at the southbound API closer to the devices. So if you want to directly work with the open flow, you have to go directly down to the network element level. But frenetic it includes a higher level language like the query language that provides effective abstraction for reading the network states. As you can see, it consists of two levels of abstraction. The upper level, which is the source level API, the programming API, it provides a set of operators for manipulating the streams of network traffic. And the lower level of the abstraction is provided by a runtime system that actually operates within the SDN controller, and it will translate high level policies and queries into low level flow rules, and then it will issue the needed open flow commands, okay, to these switches with the help of open flow. Next, let us move our attention to the applications. So you see, this is our flow. We discussed the interfaces, we discussed the network service abstraction layer, and now some of the application. The first application that we are going to explore is the traffic engineering. At a bird's eye view, network engineering is actually a method for dynamically analyzing, for dynamically regulating, and for predicting the behavior of data flow in networks. And the aim, the objective of network traffic engineering is to optimize the performance in order to meet the service level agreements. And this traffic engineering actually involves establishing routing and forwarding policies, because it deals with traffic engineering, something which is related with the flow of the data, which means routing and forwarding of data. So we need policies that are based on the quality of service requirements. Within the SDN, the task of traffic engineering should be considerably simplified, okay, because we talked about abstraction. So abstraction should be included for the traffic engineering as well. As SDN offers a uniform, global and logical view of the network, of the devices, of the switches, of the physical layer entities, and it also provides very powerful tools for configuring and for managing these network devices, these network switches. So the key area is to simplify the task of traffic engineering, and some of the traffic engineering functions that are already implemented in the SDN are mentioned here. We will not go into the details, but there are functions which focuses on the load balancing, functions that focuses on energy aware routing. For example, if you are going to deploy it in ad hoc networks or in sensor networks where energy is a main concern. And also optimization of resources with the help of scheduling mechanism. Traffic engineering, where the load on the network is going to be as minimum as possible. Recovery in case of failure. Quality of service enforcement and management. We will not go into the details, but we are going to see an actual implementation for the traffic engineering, and that is policy cop. It is going to be it is going to serve as an example of a traffic engineering SDN application. So you may be asked in MCQ that policy cop is an example of dash. Okay, so there is an example of traffic engineering SDN application, and it is it focuses on the quality of service policy enforcement. So it provides a framework, you can see, where you can enforce different policies. So the focus is on policies. That is why it is known as policy cop. The key feature of this application is that it monitors the network, the underlying network, to detect policy violations. We have a validator, policy validator. So it will monitor the network for any violation of the network of the policies. And these policies are defined as we saw in the SLA, service level agreements. And if that happens, if the policies are violated, then it will reconfigure the network to reinforce the violated policies. And this figure consists of different modules. If you count these modules like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay, 13. So 11 module and 2 databases. In total we have 13. And every module is responsible for performing some functionalities. Okay. So you can see that there are 2 databases, and databases are related with policies and with rules, nothing else. And these databases are installed. One database is installed in the application, while the other one is installed in the control plane. So you can say that this application actually uses the control plane of SDN to monitor the compliance with quality of service policies, and then it can automatically adjust the control plane rules. And also we have flow tables concept here. So flow tables in the data plane, but that is going to be based on the dynamic network traffic statistic. For that we have the traffic monitor. So let me briefly explain some of these modules. In the control plane, starting from here, the policy cop actually relies on 1, 2, 3, 4 different modules and 1 database. This is actually the control plane, you can see, and this is the data, and this is the application. So part of it, policy cop, is at the application, and part of it is at the controller, SDN controller. The admission control, it will accept or maybe it will reject request from the resource provisioning module for reserving network resources. You see, admission control, if you want to reserve a network resource, then the request must be generated and it is going to be passed through this admission control mechanism, and then it decide based on the policies whether the request should be granted or rejected. We also have the routing module at the SDN control level, and it, as the name indicate, it will determine the available path based on the control rules that are available in the rule database, rules for forwarding. And then we have the third module, that is the device tracker. It will trace the up down status of these network switches. Device tracker, these devices need to be monitored whether they are up or whether they are down. Their status must be shared with the application with the help of this module. And then we have statistical collection purposes. We have the statistics collection module, and it uses different monitoring techniques to measure different network metrics. And finally, we have the database itself. And actually, the application plane will translate the high level policies to control rules. And those rules are going to be stored in this database. And as you know, we have an API. There is the REST API, and it actually connects this control plane module to the application plane modules. These modules need to communicate with one another, and for that we have the REST API, the Northbound API. Okay, now here you can see that we actually divided the modules into two parts, or you can say we have two modules having 4 and 3 submodules each one. So there are two main components, two modules. The first one is the policy validator, and the second one is the policy enforcer. A policy validator, as the name indicate, will monitor the network to detect policy violation, and then a policy enforcer will adopt the control plane rules based on network condition and high level policies. Like, it will enforce the policies if violation occurs. And both of these both of these components, they actually rely on a centralized database. You see, this database has access from the management plane, policy validator plane, and also from the policy enforcement plane. Okay, so it has access from both the module. And this database will actually contain quality of service related policies, and these policies need to be entered to be defined by a network manager, a network personnel, or a security related personnel. Okay, let us see what are these submodules for. For example, we have the traffic monitor module. As the name indicate, it will determine appropriate monitoring intervals, or you can say different metrics that need to be monitored is the responsibility of this traffic monitor module. And then we have the policy checker to check for policy violation, because this submodule is for policy validation. So we need to check whether the policy is defined by this person has been violated or not. So it check for violation. And how it check for policies, from where it get the input. So you can see it get its input or information about the policies from this database. And then we have event handler. It will examine violation events. If an event occurs, then we need to inform it and reinforce those policies. So the event handler actually examine the violation events, and it then automatically invoke the policy enforcer module by sending action requests to the network manager. Hey, some policies were violated. Okay, so it generate like an event and then inform the manager to take appropriate action. And then we have the Topology Manager, which deals with the topology. It actually maintains a global view of the network. And then we have the Resource Manager, which actually keep track of the allocated resources. And we have the resource we have the resource manager which keep track of the allocated resources, and we have the policy adapter which need to be contacted by this event handler. Okay, and it actually consists of functions, different type of you can say actions for policy violation. For example, if policy number 1 is violated, then block the device. If policy number 2 is violated, then remove the device, things like that. Okay, so different types of policy adoption. So this is the actually the policy cop architecture. I forgot to explain the resource provisioning, which is directly connected with the database. And this module, as the name indicate, either allocate resources or release resources based on the violation. Violation occur, event handler inform the manager, policy adapter came into action, and then it either remove that resource or do something else. So resource provisioning is actually later on. For example, if you want to add a new resource, or if you want to grant access to the resources to a new person, to a new device, then you can actually use this module, because its responsibility is to allocate more resources, or in case if a policy is violated, then it will release existing resources. So this is the whole architecture for the policy cop. Our next application is related to the security. We will not go into the details of security because it's in itself is a huge topic, but application in this area actually focuses on two things, or it has two objectives. The first one is to address security concerns related to the use of SDN. Potential for new vectors of attack. Okay, like there are different types of threats for a network, and they occur at any of the level. We saw that we have three layers: the control layer, the application, and the data. So threats are possible at any of these three layers, or even this is possible that the communication that happens between these three layers with the help of APIs and with the help of different interfaces, that are also at risk, because you cannot violate the security and privacy issues from any type of network. So SDN is not an exception. Security risks are there which are related to the use of SDN, and it could be related with the individual layers, or it could be related with the communication that happens among these different types of layer. So SDN applications are needed to provide a secure use of the SDN itself. That is the first goal, to address security concerns that are related with the use of the SDN. The second goal is to use the functionalities of the SDN to improve the network security in which it is implemented. So although SDN presents new security challenges for network designer, for manager, for researchers, but it also provides a platform for implementation of centralized security policies and mechanism for the network. So on one side it is on risk, on the other side we can use the functionalities of the SDN to improve our network security, because SDN will allow the development of SDN security controllers and SDN related security applications that can provision security services and mechanism. An example of an architecture that actually focuses on this second objective is known as Open Daylight Distributed Denial of Service application. This Open Daylight Architecture DDoS application actually uses the existing SDN functionality to improve the network security. How? Let us see. First, a few lines about this architecture. It is a project with defense for all, and it is like an open SDN security application. And this defense for all project is actually implemented within the Open Daylight architecture. Okay, so this, you can say this is like a built-in component of this Open Daylight project. And the name is distributed denial of service, and this is a type of attack if you are familiar with it. If not, you can Google it. So using the Open Daylight SDN controller, detection and in some cases mitigation of this attack is possible. This technique actually uses a common approach to defend against the distributed denial of service attack. How it actually deal with such type of attack? It deals with such type of attack by collecting information about the traffic, or you can say by collecting statistics of the traffic. Normal traffic baseline of the protected objects are built. Like you record information about the normal traffic, and then in the second phase, detection of the distributed denial of service attack patterns are recorded. For example, if there is an attack, then obviously the traffic is going to be different from the normal traffic. Okay, and then once the attack is detected, the suspicious traffic can be blocked, or they can be diverted. Okay, so like a three-step process. First, you collect statistic about the normal traffic. Then if there is a suspicious traffic pattern, you detect it and then you block it. And this figure actually shows such a scenario. You can see that the underlying SDN network consists of a number of data plane switches, and these switches actually support traffic among different clients and server. On left side we have clients, on the right side we have server, and there is a traffic between the client and the server, and that goes through these data plane switches. Now this distributed denial of service application actually works at the application layer, or it operates at the application layer, but it interacts with the controller. You can see we have like the defense for all application. We have an interface which is based on the REST API, and the user or the network administrator or security, whatever person it is, he's able to use this application, and it itself interact with the controller over Open Daylight controller. You can see here, because it is implemented inside the Open Daylight architecture, so this application will actually make use of the Open Daylight controller through this API. And actually this application support a user interface for this network manager that can either be a command line interface, or it could be like, if it is a REST based API, so that is also possible. So actually you can define different policies as well for controlling different types of attacks related to the distributed denial of service attack. And you can see we have different components like the attack mitigation system, which in short is known as AMS. So actually this application will monitor the traffic of all all these switches, or it will monitor the traffic that goes to that goes through these switches. And in the application, it is mentioned in the description of this application that if the real time traffic exceed 80% from the threshold defined, then it is assumed that an attack has been occurred on the network. So we will not go into further details of this component, but this is how it happens. We have traffic flows between between clients and servers. Normal traffic is recorded, and then if an abnormal traffic flow is observed, then the attack mitigation system is consulted to either block that traffic, or if that traffic is legal, then it will remove that block from that traffic flow. Our next application is the big data over SDN. Now we are going to talk about data center networking. Big data is related with the cloud and with the data center. So we have already talked about these concepts in our previous lectures, but let us see them again. Cloud computing, big data, large enterprise networks, and information-centric network, they all strongly depend on highly scalable and efficient data centers. So cloud computing is related with the data center. Big data is related with the data center. If there are large enterprises, they are going to use data center. Even small enterprises, they are also shifting to the data centers concepts. They have either their local data centers, or they can purchase the services of a data center by using utility model. So the key requirement for data centers is that they are going to be highly availability is going to be high, their flexibility is going to be high, their latency is going to be low, their quality of services is going to be high, their resource utilization is going to be intelligent, they need to reduce the energy consumption, and they need to improve the overall efficiency of the network. These are the goals for the data centers. Okay, so with traditional network architecture, many of these requirements that I just mentioned, they are difficult to satisfy. That is why SDN offer a substantial improvement in the ability to rapidly modify data centers configurations to ensure efficient operation of the network. We need a way to shift data center from traditional network architecture towards the SDN based architecture. For that, we are going to study two examples. The first one is related with the big data. And everybody is talking about big data. It is everywhere. Now, our problem is to use the SDN concept to optimize data center networking for big data applications. For that, we actually need three things. We need to leverage the capabilities of the SDN. First point. Second point, there is the characteristics of the structured big data. That is also important. And the third point is the use of the optical circuits. So capability of SDN, you are quite familiar with that. The second component, like the structured big data, is something new. What is that? What do we mean by structured big data? Let us see. Actually, the structured data, it depends on the existence of a mature data model. Like the most traditional form of data storage, for example, Excel file, SQL databases, where the data is stored in tables, they are example of structured data because they have a matured data model, how the data is organized, how the data is stored, how the data is accessed, and so on. On the other side, the unstructured data is information that either does not have a predefined mature data model or is not organized at all. and that is going to be very much difficult to understand this unstructured data by using traditional programs. Okay, and common example are like you have a data that include audio files, video files, non-SQL databases, etc. So to search information there is going to be difficult, time consuming, and so on. So structured data is important, especially for big data application. So that is the second thing that we need to consider. An optical circuit is the third thing that we need to consider. Optical circuit is like related with the opticals transmission, like any piece of circuit switching equipment that works between the fibers, and why we use it in order to get better control of your devices, your physical infrastructure. These devices are going to reduce the multi-tenant data center reconfiguration times. This is a concept which is related with the data communication. We will not go into the details, but for us the important thing is that they will enhance the performance of the SDN. So these are the three things that lead to the big data over SDN deployment. So structured big data application, that is important because as I just mentioned, processing data according to a well-defined computational pattern that will lead us to better performance. And it also have a centralized management structure, a centralized management control over your data. Okay, so optical switches on the other hand, they will provide us greater data rates, and they will reduce the cabling complexity as well, and also energy consumption in some of the cases. So overall, these three components are going to improve the application performance. Now this figure actually shows a simple architecture that is composed of SDN switches, but this is deployed in a data center concept. Here the OCS is the concept that I just mentioned, the circuit switch, and O stand for optical, C stand for circuit, S stand for switch, optical circuit switch. We have like the SDN controller. We know about SDN controller. Actually, in this case, the SDN controller is connected to two switches, two types of switches. You can see it is connected on the edge. It is connected to the OCS, and on the other side, it is connected to the Ethernet switch. This is a simple Ethernet switch. However, you can see that all these switches are actually controlled by this SDN controller. That is why the SDN controller actually manages the physical connectivity among these switches. But we have optical circuits as well, and we can configure this optical circuit switch as well. It can also manage the forwarding between these switches by using different forwarding rules. Well, some of the concepts are related to the big data, to the cloud computing, so I would try to avoid the details because that is going to be a discussion out of the context. But it is important to understand because at least a one-line introduction to these. For example, we have Hadoop. You can see that the SDN controller in this case is not only connected to the switches but also to a new component that is the Hadoop scheduler. Actually, it forms queues of jobs to be scheduled. And Hadoop itself is a huge topic. If you are interested in cloud computing, in big data analytics, then you must have to go for the Hadoop. And I have a video about Hadoop installation on Linux operating system as well. You can see that as well. We also have another component like the Hbase, Hadoop base, and this is going to be a master controller of a relational database. It will hold data for the big data applications. No further details. Our SDN controller is also connected with the Hbase. And for cluster purposes, we do have a Hbase cluster manager, and it is like an open source software package that provides scheduling and resource allocation services across distributed environment. So for centralized, we have the setup. For distributed, we have the setup, and our SDN controller is connected with them. So if you want big data to be controlled over SDN, this is a basic integrated approach. You can see the SDN controller is actually able to be connected with the Hadoop, to be connected with the Hbase, and to be connected with the cluster manager, which is Hbase. Our next application is related with the cloud networking. Cloud networking over SDN. And cloud network over SDN is another application area for SDN, but to discuss that, we need to consider an example framework or architecture that is known as Cloud NAS, and it stands for Network as a Service. Now we are talking about cloud computing. In cloud computing, there are different models like application as a service, like platform as a service, like infrastructure as a service, security as a service, and so on. So one of them is NAS, which means network as a service, and cloud is cloud. So cloud network as a service. It is actually a cloud networking system that exploit open flow SDN capabilities to provide a greater degree of control over cloud network functions by the cloud customers. It uses primitives that are directly implemented within the cloud infrastructure. So this figure actually illustrates the sequence of events that actually happened in this framework. So there are 4 sub-images. Each sub-image represents an event. Let us see these events one by one. The first one is specify user requirement. So we have a cloud customer, and he uses a simplest policy language to specify network services that are required by the customer application. And these policy statements are issued to a cloud controller. So you define the policies related to the network, and then you issue those policies to the network controller. This is simple. Second is communication between the cloud machines itself. Like here we do not have the user anymore. So the cloud controller actually maps the policies entered by the user. So here the main thing is mapping. Now we have the policies that were entered by the customer, by the user, and then the mapping occurs here. So the cloud controller actually map the network policies entered by the user into a communication metric. And this metric actually defines the desired communication patterns and network services. You can say now the policies are converted into a language that is understandable by the devices. The metric is used to determine the optimal placement of these virtual machines on the cloud. I will not go into the details, but to give you an idea, in cloud the resources are provided on request. The provision of resources is on request. If you need more resources, you request for more resources. If you do not need those resources anymore, you can release those resources. So here, reallocation of resources is something which is related with the optimal placement of the virtual machines on the cloud server. And this allocation is actually done based on the knowledge of other customer requirement, because the concept is known as multi-tenancy. So the resources are not actually allocated to a single user, they are allocated to multiple users. So there must be knowledge of who else is using those resources for efficient utilization. And then now we have mapped the policies into metric. The next thing is to issue those policies. So there is a logical communication. You can see that the metric is actually translated into the network level directive for data plane forwarding. Here we have the actual resources. The policies were issued by the customer, they were translated into the metric, and then they are forwarded as directive for the data plane forwarding elements, the switches. So the customer virtual machines instances are deployed by creating and placing the specified number of virtual machines. So here is the logical communications that occurs between the matrix and that occurs between the switches that are actually programmable devices that you can control, and the information were provided from the communication from the matrix, the communication matrix. And finally we have the last scenario in which the network level directives are actually installed into the network devices with the help of OpenFlow. So you can see the user actually want this thing. Okay, he want to communicate with the network devices, but first the policies were issued to the controller, then it were mapped into the network into the communication metric, and then the communication metric was translated into network level directive, and then they were actually installed in the network devices with the help of OpenFlow. So this is actually like abstraction. This abstract network model seen by this customer, it consists of virtual machines and a virtual network segment that actually connect these virtual machines together. Okay, there is another view of the above scenario. It actually provides an overview of the architecture that we have studied, known as the cloud NAS, network as a service. You can see it has two main components. That is the cloud controller that we just saw in the above slide, and we also have a network controller here at the top. So two components. The cloud controller actually provide a base, like we have the infrastructure, the physical switches, so it provide a base for the infrastructure as a service, IaaS. And the user can communicate, or you can say send request for setting up these virtual machines instances. Okay, so he can send or he can communicate with this cloud controller, and the cloud controller actually manages a software programmable virtual switch on each physical server in the cloud. So the cloud controller actually construct the communication metric as just we saw in the previous slide, and then translate this to the network controller. The network controller actually uses the communication metric to configure data planes for these switches. Okay, so we will not go into further details of this scenario, but this is how the NAS architecture actually it is, because most of the concepts, they are related with the cloud computing, and it would be difficult to understand them, like the virtual machine concept, hypervisor concept, infrastructure as a server, as a service concept, and things like that. But still, if you are interested, you can dig into the topic. Finally, we have the topic, another application area, there is the information centric networking. I will go quickly to this slide. Actually, the information centric network, or ICN or CCN, sometimes it is known as CCN, content centric networking. It received attention of the researchers in recent years. the basic concept is that we have a traditional host-centric network paradigm, and now we have an information-centric network paradigm. In the traditional host-centric network paradigm, information is obtained by contacting a specified named host. Okay, like you have the IP addresses, you have the port addresses, and things like that. So the basic idea of ICN is to decouple information from its sources. Information sources can place an information user can actually find information anywhere in the network because the information is named, addressed, and matched independently. So the focus is on information, not on the specific IDs. Instead of specifying a source destination host pair for communication as we saw in the traditional host-centric networking, a piece of information itself is given named. So when a request is sent, the network is responsible for locating the best source of information that can provide that desired information instead of any specific host. So the concept of ICN is emerging, but the problem is that our traditional networks, they are challenging because the existing routing equipment would need to be updated or replaced with ICN concept because their routing concept is different. Here the routing need to be happen based on the information, not based on the source address or destination addresses. And also the ICN shifts the delivery model from host to user to content to user. In the traditional model, the flow of information is from host to host, while here the flow of information is from host to content. But traditional networks, they are not ready for ICN concept. So SDN has the potential to provide the necessary technology for the deployment of ICN because it provides for programmability of the forwarding element as a separation of control and data planes. As we can see that in the SDN we have a separate layer for forwarding layer and a separate layer for control layer for controlling the devices. There are different approaches that have been proposed for ICN, how it can be merged with SDN. One of the approach is mentioned here, and that is called CCNX. It is actually an open source project, and a number of implementations have been deployed experimentally. Actually, there are two types of packets in this CCNX architecture. One type of packet is known as interest packet, and the second type is known as content packet. A consumer requests content. Okay, you are a consumer, you request some content. For that you need to send the interest packet. It's like the request packet. Now any CCN node that receive that interest packet and it has the named data, it is able to fulfill the request that is made by the user. So it will respond with a content packet, a response packet. The content satisfies an interest if the name in the interest packet matches the name in the content packet. So if a CCN node receive an interest, but in case it does not already have a copy of the requested content, for example, the server receive a request but it does not have that information available, it may forward that interest packet toward a source for the content. Okay, you can use forwarding table that will determine which direction to send the interest packet. Multi-hop forwarding is there. So the basic operation of CCN node is similar to an IP node, but the difference is that CCN node receive and send packets over a concept that is known as face, and it is like the port. So a face is a connection point to an application, or it could be a connection point to another CCN node. Here, if you want to use the CCN concept, the CCN node, you will need an abstraction layer, and that abstraction layer is known as wrapper in this context. So the central design issue with using SDN switch to function as an ICN or CCN node is to use that layer. But here we have a challenge. The challenge is that the packets that we receive at the switch, they have IP addresses, and we need them to deal with the names, with the information. So for that we have to modify the IP packet. Especially the destination IP address must need to be updated. So the ICN router actually forward the packets based on the content name, and there is a field in the IP datagram IP packet that need to be modified. Okay, so actually this figure shows the overall architecture of this approach. We will not go into the detail of the ICN network because itself it is a huge topic. Many terminologies are new for us. Okay, but the abstract level view of this architecture is that we have a CCN node, and that is like it contain a open flow switch, and then it contain an abstraction layer that is called the wrapper, and then we have the CCNX application installed on top of it, and these are connected with the help of face interface. Actually this face or this wrapper pairs a switch interface. Below we have a switch interface, so it pairs a switch interface to a CCNX face. Why we need them to be paired? Because at the top level we have information named access by name, but at the bottom the switches we have the IP addresses. So we need a mapping from the name to IP addresses, and from the IP addresses to name, or even port number could be there. Okay, so that is why we need this abstraction layer to hide the details of the mapping, and for mapping we have the face interface and things like that. And also we have the forwarding table in these OF switches, but they need to be updated. They need to set to forward the packet based on the content, not on the IP addresses, but we will not go into further details. Okay, so this is the whole architecture. And also we have like the controller. The SDN controller has been modified with 3 different modules, and those modules are like the measurement, optimization, and deflection. The measurement actually, as we are talking about the contents in the information centric networking, so content popularity can be measured for statistics purposes, like which contents are popular, so that they can be measured for statistical purposes. And then we have the optimization module, which will actually use the list of most popular content. Okay, so the most popular content that we measured are provided as an input to this module that actually list the most popular content. For optimization purposes, it uses different optimization algorithms, and the popular content is even cached in the node, okay, for future references. And then we have the deflection module that actually uses the optimization results to build a mapping for every content between the contents name and outgoing interfaces and things like that. But I will not go into the details of this CCNX architecture. You may skip this for the lecture, for the physical class. Okay guys, so this was about today's lecture, and it was about the application plane of SDN, different application, network abstraction layer and interfaces that we discussed in this class. Thank you so much. Take care and goodbye.